Okay. Now we are at the bottom of the decision tree. You've got the big tree we did up here. Then we did our optimization of the hyperparameters.
We still can't see the screen.
Oh, we think today was Monday. See there. Look. Okay, here's our giant tree where I did no limitation on the tree. And naturally, as you can see, it doesn't give you a lot of readable information. So we took the optimization of hyperparameters, get a lot more interesting tree, a little more clear cut. So I messed around with the figure sizes and you get this. Now, the way this works is you can step down through every decision path, sticking over to the left. Eventually you get to the leaf nodes, which are down here. And of course I can't blow this one up enough, but if you start over here, you can see there's no contract because contract's less than 0.5, less than or equal to, and contract was 0 or 1. Monthly charges, less than or equal to 0.96, which means monthly charges were 0 and 1. So I'm coming down the faults. Now I'm going to stick over here. I'm back to contract again. You can reuse these. Monthly charges, tenure, and of course I'm down here at the not churn. And I've got a really clean, it's not pure, but it's 108 churning, not churning, and 1 churn. Well, the opposite of that would be very dense blue over here, which would be a churn. And so you can literally walk down. So if you consider, when you're thinking about this, this will do it for you because you can consider the split at the root node and the 2 splits in the first row. The logic for each leaf of the tree is the same. So first look, now remember, the system, the algorithm decides on what it's going to split on first to get the most amount of information gain or a decrease in entropy. So what it does, it checks all the customers. 4,100 did not churn, 1,496 did. That's its split with a contract type. Now, contract variable less or equal to, you've got 3 choices here. 0 month to month, 1 is 1 year, 2 is 2 years. And so less than or equal to, it means you've got the month-to-month contracts, and if it's greater than 0.5, it gets the 1 year and 2 year together. Just coming down, walking this through. So then I'm going to split the month-to-month from customers with longer term. That's great. That happens to be the length of the contract is the most important initial factor in predicting churn. Okay, so I'm looking at node purity, Gini and purity, how mixed up are the classes? A Gini of 0 means I'm pure, all samples in one class, churn, no churn. 0.5, completely still mixed up. Okay, 0.39, somewhat mixed, naturally. Here are your samples. It's not churn, so 4,100 didn't churn, 1,496 did. After the first split, pick up the left node. Again, follow the logic. Let's see, yeah, left node. Fiber optics encoded no and 1 or yes. So there's your Gini index 0.3. They're still mixed. 2,300 not churned, 715 did. So I've got month-to-month contracts because I'm coming down that path. Now I'm going to check to see if they have fiber. Who picked the fiber? The algorithm. 0.32, somewhat more pure than 0.5. 2,300 did not churn, 715 did. Majority is not churn. So you come down. Now you're in the right node. Working your way down to the bottom. The system picks monthly charges. There's your Gini index of 0.19. Starting looking good, getting closer to 0. 2,370 are not churned, 181 did. So longer term contracts, they split on monthly charges. Less or equal to $93.68. Okay, Gini index, getting better with purity, and majority class is not turned. So Now you're talking about business sense, which is going to your business problem. If you decide to do a decision tree, some of you may go straight to random forest. Customers in longer contracts, much less likely to churn compared to month-to-month customers, and then you get the 23% churn rate. That's how you walk down. Now, what have you done? Every one of these leaf nodes down here at the bottom have a particular path coming down. All right, so here's 2, 4 is 8, times 8, 64, etc. So I've got a large number of these leaf nodes, and every one of them has a path just like this. It takes all the way to the bottom, and again, what you can do, if you're really insistent on looking at the leaf nodes, you can say, all right, I've got 40 and 10 here, my figure size, then I went 20 and 16. If you really want to blow this thing up, you can and make it larger, and then you'll have a bar down here to go back and forth and look and see what's down at the bottom. All I'm trying to do is churn or not churn. So you get done with that. That just shows you how the logic works. Model performance, just like we've done. Training and test. Training actually 0.8, test actually 0.8. Life is good, no overfitting. And if we're overfit, your training actually would be very high, your test actually would be lower. Pretty standard. That's the way that works. Now, decision trees are fairly straightforward, but remember, random forest does multiple decision trees. Okay, same data set we've been using, standardized nicely, same size. I just back check to make sure everything comes through. You've still got to identify your independent variables and your dependent variable. This is a shorthand method to do that. Split your data. Okay. Next thing you do, you pick your random forest classifier. You bring it in here in your code libraries. By the way, if you forget to do that, clearly, which I've done, you'll get all kind of errors, and you'll realize you forgot to import it, but you're trying to run the random forest classifier. Okay, just make sure it's in your code libraries. All right, now, in estimators, this is your hyperparameter that you've set. So what you've got, here's a random forest classifier, CLF. I just put identified CLF, your classifier. I'm going to use 20 decisions. I want to create 20 decision trees. The example we showed last time, we only did 4. So you can pick any number here. It's green, so you know you get to change it. So this is an interesting situation here because you get to figure it out, because each tree is going to vote because you're in classification. Now, if you increase the estimators, you're going to get better predictions, but it's going to grind a bit. Slower training means your computer might keep going a little bit. Now, max depth, you get to figure out how deep the level of the tree can go. If it's set to none, it can grow as deep as they need to. Then, of course, you set, if you want to pick 3, you get 3 levels of decisions. And if you limit the depth, you can prevent overfitting, but you might miss more complex patterns. This is data sciencey stuff. I left it all out, if you'll notice. I didn't do anything on max depth because I wanted to see what happened. And so you just do very next thing. You've brought your classifier in, max depth equals none, let it go. Then you're going to fit the data naturally with your training data. Then you can do your prediction with the test data. Exactly the same as you do the other parameters. Okay. Then you get to go right into evaluation, and you're going to get this classic map here if you decide. My training, 99.29%. Okay, that's much higher than a decision tree. Random forest is more powerful because I've got random trees. Okay. Test data, 79%. I'm overfit. Okay. I've learned, the algorithm has learned the training data so well that it's not generalizing to the test data. That's fine. It's just what you get to deal with. This is the exact same confusion matrix that we had the previous ones. It's not that far off with true positive, true negatives, and so forth. Now, when you're in random forest, it's kind of interesting if you take a look at the feature importances. So you set up importances as your variable. Then you want to sort them in descending order. And then I'm going to use X dot columns instead of DF dot columns. Long story about that. That's computer sciencey. There's your figure. You can add the bars and feature names and show the plot. So you're going to print it out. So you're going to get this. Again, this is your code. So I have feature importance. Down here is the actual numerical, 0.21, 0.19, 0.16. Notice total charges, monthly charges, tenures I come across. Okay. That's 0.4, 0.56, 0.64, 0.7, 0.75, 0.78, etc. It would be real nice if this added up to 100%. Okay. Just check it. Okay, so then I want to get the feature names. I want to put them back in. And so this is a way to do this with percentages. If you like, it's the same thing we did up here. I just put it in case you liked it. Okay, what have you got? Relative importance of each feature and predicting customer churn. It's possible that you could look at something like this and say, well, where do I get the top 95%? Well, right about here, give or take. But you could actually play with this if you're in a situation where you had a boatload of features. Some of you are going to have that, and so if you get 50 of these things, you could always just decide to truncate and say I accounted for 80%. Relative importance, higher percentage, more it helps the model make accurate predictions about churn. More than likely, your business users, especially at managerial levels, are going to think to themselves, everything from here down is 2%, okay, or less. So when I get past, say, security package or maybe fiber, then, where are they going to start putting their money? Right here. Okay, what? For incentive packages. I want to keep you from churning. All right, that's where I'm going to spend the money. Maybe the contract's off. Obviously, length of time they're with the company, that's great. Monthly charges, right up there in total charges. They're your top two. Yeah.
Would you want to get rid of all of the 2%, to get it to 80 or 90% to fix the overfitting, or just to identify where you want to be?
Where are you going to put the resources?
Okay.
Yeah. You're overfit, but that's, in this particular case, what you can do is, one of the things we're not doing it here because it does get way off in data science, you can start messing with your data split. Instead of 80-20, you can try 70-30 to do that. I wouldn't do that. Okay, it's fine and dandy if you guys are overfit because we're not dealing with fire hoses here where the data keeps coming in. Okay, these are static data sets. Just say I'm overfit, and one of the reasons is it's random forest. It's also that I have only 7,000 instances. And I've got a lot of features for 7,000 instances. Okay. If you do decide to do that, just out of curiosity one night, dump this bottom group down here. You say, I'm just going to use fiber and above. You can always rerun the random forest with just those features and see what happens to the overfitting. top 3 features account for over 50% of the predictive power. Theoretically, you could just go with the top 3, run around and farce again. It'll run really quick and you'll get you'll get less overfitting. Mostly though, listen, somebody's got to write the checks. Okay, executive sponsor, somebody's got to write the checks to do this. Somebody's got to sponsor what you're doing, and they're going to be very interested in, now I'm talking about in the real world, everybody's worried about churn. Y'all know that. It usually comes up in wireless companies, of course, but they're all concerned about it. So then you say, okay, how can I prevent that? We talked about that endlessly with decision tree. Okay, decision tree, we'll do support vector. All right, what do we pull in? You pulled in, let's see here. Okay, in this particular case, you're going to come out of sklearn, import data sets, support vector machine, and metrics. Okay, so make sure you've got that. Do the whole, everything's the same, all the way down to right here. Split the data, you've done that. All right, here's your classifier. This kernel is just, I'm going to ahead and describe some mathematical technique that lets your group split. There's all kind of kernels. I just picked RBF, which is fine. I'd recommend that. This again, that's data science. This influence, each training example has each instance. If we put a gamma 0.01, each example has a lot of influence and the model considers a broader neighborhood of customers. Again, you've got a support vector trying to split them. Large gamma, each instance only influences nearby predictions. Again, we're off in computer science. Just go ahead. Your CLF classifier here is your support vector machine. That's your kernel, and just use gamma 0.01. Obviously, you guys can drive depth on any of this if you like. But look, this is algorithmic literacy. That's all it is. Okay, you're not going to be doing this in the real world, but you are going to be able to talk to the analysts who are. Okay, but I tell you what, 80% of every project's data cleaning. Okay? We beat that to death deliberately. You're in charge of data cleaning, by the way. They're going to do it, but you're going to have to explain it to them. They'll say, this looks like clean data to me, and it may, but they'll have to come to you to decide. Okay, so you do your fit with training data, of course. Do your predictions with the test data. Go straight in to find out what the metrics are. And we're looking pretty good. Overfitting, 79, test accuracy 80, that's great. Very similar confusion matrix. Your overall actually 80%. Okay. If you'll notice, and you're going to get this probably, because you've got static data sets, your confusion matrices are going to be pretty close together. You explain it once, you don't have to explain it 12 times, okay, or have many algorithms that you run. However, if you do get a difference, like in this particular case, random forest looked really interesting. It's different than what we're getting here because it's an ensemble method. Very powerful. So that's something that, this just happens to be another algorithm. You got very similar results as you would expect. All right, K nearest neighbors. Okay, identify the variables, come down, do your splits, data split, then you're going to import, okay, nearest neighbors classifier, nearest neighbors here at 3. You choose. Remember we talked about, we were going over this before, it'd be better, I guess it'll finish running in a minute. It will be better if you picked an odd number. There's no reason to give it a chance to come out with half and half. Okay, so we're picking 3. Do your fit with training data, do your predictions with the test data, run straight into accuracy. Just run this runs the algorithm, and we get 74.8. Confusion matrix is kind of a little more, at k equals 3 is confused. You're getting lower true positive, true negatives. Okay, so it's worth taking a look at that just out of curiosity. Well, then what you can do, you can say, well, I just picked 3 arbitrarily so you could watch it run it. Well, you can also run some code to figure out the optimal number of neighbors. Okay, it's going to use cross-validation, don't worry about it. Here's your code, and you can get some graphs down here that plot the accuracy versus k, k being the number of nearest neighbors. Come down, I said, what I'm going to do is I'll just say nearest neighbors equals 7. All right, well, I get this graph. Right up here, this is about 7 right there. And it looks like around 13 is about my highest. The highest I get to, the earliest. Well, that's not bad. Accuracy is 0.78. So then we'll try 5. Get a chart like this, and it's still over here at 13. About the same accuracy. Try 9. Same code, just switch it over to 9. Now you're looking at still about 13. So I just ran these 3, so you get to pick it. If I had to look at this, when I got past the second one, I probably would go ahead and run it with nearest neighbors equal to 13. Just, out of curiosity. But what do you have? I'm only at 0.79. So the accuracies are all the same going down through there. I bet if you ran it for number nearest neighbors equal 13, that you'd have very much close to 0.79. Okay, so you check for overfitting. Training's 0.82, test is 0.79. Not bad. It occurs to me there's a confusion matrix I ran there. You can also run a confusion matrix with every one of these Ks. You get to pick it. By the way, you get to choose one. You'll see how this is going. It's all the same as the way that it works. In just a minute, it's going to kick me out and tell me I've got too many sessions running. Okay. That's it for supervised. Now, you've been through all the supervised, been through regression, all the supervised classification, and now you've got unsupervised, which we're only running k-means clustering. Aha, see what I mean? You get this, if you run too many sessions, go to manage sessions and get rid of those. Then you close it and you get to do runtime again. Okay, now I just checked DF head just out of routine, just for my own benefit. Then I'm going to use all the variables except churn. Okay, that's going to be your clustering. So you do this, you're going to define your variables here. Drop churn. Now, next thing you do, I've got to figure out the within cluster sum of squares. Okay, range of clusters 1 to 10 here. K-means algorithm. The Wix within cluster sum of squares. Okay, this is the code for that, and you're going to plot it. Remember, we talked about the elbow. Okay, get a severe drop here, drop right there, then come right on over. Well, you really got a couple choices here. All of us know that we're dealing with churn and no churn. Well, clearly that's your big drop. There is a possibility in another data set that you could have picked 3, no more than that, because that's where your drop is. But in our case, we know it's churn, no churn. So you pick 2, choose the number of clusters, K equals 2. Then you go ahead and you perform the K-means clustering. Okay, so I picked 2 as the number of clusters. K-means, you're going to fit, and then you're going to go to here to labels, and you're going to run, now notice, I'm assigning cluster labels generated by the K-means algorithm, and then the inertia is the total square distance between each data point and the centroid. Remember, we had the centroid there, and the lower values of inertia means tighter clusters. This is great news if it's nice and low. Now, K-means inertia here is about 1 million. Okay? Not quite sure about really what's that mean because of the various, the feature orders of magnitude. So now I'm going to look for silhouette scores. It ranges from -1 to 1. 1 means that I've got the data point that you're looking at is well clustered and far away from the other clusters. That's great news. 0 is in between 2 clusters, and -1 means it's in the wrong place. Okay, so I want a silhouette score of close to 1 naturally. 0 means I've got poor separation, and negative score means there's something, let's just say your data is highly intermixed. Okay, all right, what have I got? 0.66. That's okay. Now I've got to do the cluster labels. Now, there's your cluster labels. I'm going to assign them the original data set, calculate the centroids, and then I need to create another data set to hold these centroids because I'm excluding the cluster column. Long story there, but create that centroid data set. Now, you got to display the centroids. Why? Well, look what you've got. Got a 0 centroid, which is no churn. The 1 centroid, which is churn. You take a hard look at gender, there's no difference. Okay, so you don't have any significant contribution there. Senior citizen, partner, dependents, and so forth, all the way over across all the features. Okay, now, so you come down here to your explanation. Now, senior citizen, cluster 0, 21.2%. Where's senior citizen? Okay, those are the centroids themselves. And what have I found down here? It's a, there are fewer senior customers in centroid 1. Okay. Now, Then do partner, it'll give you dependence, it'll give you a 0% and a cluster 1%. You come down and you say, well, here I am with the insight. So cluster 1, high churn risk, cluster 0, no churn, stable customers. This is a retention strategy you can use for churn. Loyalty programs, long-term contracts, customer support, and then you want to upsell more premium services, bundle deals, and so forth. These are people who are going to stay. So 0, stable customers, longer tenure, more services, higher changes, and higher charges. And then the churners, you get shorter tenure, fewer services, and lower charges. Okay, you would expect that. I look at my cluster analysis here, and so there's your 12% churn rate with the people who are going to stay, 38% with people who are going to leave, and you get to work your way through on, is this actionable to, you're happy with these people, okay, you don't want to waste any money on them other than maybe offer them premium services to upsell them. And here, you've got these characteristics, and you get to figure out what can I offer in here to keep them around. And it's an interesting thing there because the cluster analysis doesn't give you exactly what you had before. So I just wanted to go ahead and run the same data set. So it's just an interesting algorithm. For you guys that decide to do the unstructured you don't necessarily have to leave that with, you're going to be pretty sure with what your groups are already, but look at that within cluster sum of squares before you do anything else. Okay, neural networks. You're going to get to do one of these. Artificial neural networks, also called neural networks. These are virtual neurons, which is software. They work in parallel. The idea was to get at the way the human brain works, which is our brains are massively parallel. You've got input nodes. Notice they don't have any biases or activation functions. They route data to the nodes in the first hidden layer, then you go to the hidden layers, and you come out to the output nodes. And I'll show you all that. The weights, these are numerical values of the neural network that determine the strength and direction of the connections. Okay, we'll be doing that. So you've got the input layer, one or more hidden layers, and one output layer. They're only called hidden because they're located between the input and the output layers. Deep neural networks, multiple hidden layers, hyperparameters, again, we're right back to that. You set these before training and control the learning process, and these are your hyperparameters. How many hidden layers, number of nodes in each layer, the learning rate. Now, that's how much that the neural network is allowed to change the parameters after each training iteration. Parameters you don't set. These parameters are determined by the neural network. You set the hyperparameters. You guys picked that up in analytics, didn't you? Okay. Well, here's the deal. When you're setting up your neural network, go ahead and feed your first 5 rows of your data set into GPT or Claude or whatever you're using, and then ask the large language model to help you with these hyperparameters. In other words, I'm running a neural network. Go ahead and say it's feed forward back propagation. Put that in your prompt. On this data set, first 5 rows, you can get that with df head. and then you say, tell me, take the role of an experienced data scientist and help me with number of hidden layers, number of nodes in each layer, at the learning rate, and the activation function that we should use. Now, here's what you say. That thing now knows what your data set looks like. Okay, it's got the fact that you're running feed forward back propagation, needs to know that. It's putting itself in the role of an experienced data scientist, and you say, tell me step by step. Okay, it's going to go ahead and regurgitate all that to you right here. You just say, it'll say hidden layers and whatever you just told it to do. Say you want an explanation of each one of those step by step. Okay, that's the prompt. In other words, you're not doing the neural network by yourself. Okay, there's the input layer. That's a node. This is just a piece of software right here. So your data point comes in. It's a feature. And you have, in this particular case, these are output connections. I just shown 3. You can have many. Okay. By the way, these are connections. They each have a weight, and they go to the first layer of the hidden layer. The first layer of the hidden layer, first hidden layer, and it'll have the number of nodes that GPT told you about would be the best to have. So you can have 15 of these depending on your data set. I'm only showing 3. Okay, now hidden layers. You've got connections coming in, each with a weight. Inside this software, this node, you have a bias and an activation function. And then you're going to have output the connections that go to another hidden layer or to the output layer. But you will have multiple hidden layers. My suggestion is go ahead and tell the language model to go ahead and give you multiple hidden layers. Okay, you'll have a better convergence. Okay, your output layer looks like this. You have connections coming in from the last hidden layer. You have a bias and activation function. You have an output connection. Okay. Now, this is generic. Feature, feature, feature. These input nodes just direct the data that comes in to the first hidden layer. I've only got one hidden layer here, and you can see they're heavily interconnected. And then output layer over here. Pretty standard. You will not have one this simple. Okay, so what's a bias? Okay, it's a parameter determined by the neural network, not by you. It's not a hyperparameter. It's a numerical value that determines the difficulty of a neuron firing. What does that mean? The neuron, which is software, it's processed its inputs. Okay, what have I got here on this one? All right, the inputs, I've got 3 inputs coming from the 3 input layer. So it's dealing with those 3 inputs. So it's processed those, and it's decided to send a signal to the next layer of the neural network. It has to be active enough. In other words, we'll talk about the activation function in a minute. But the bias determines the difficulty of the thing firing. Okay. We also have activation functions in these nodes, the hidden layers and the output layer. It transforms the input signal of the neuron into the output signal. Now, the activation functions in a node determine the output of that node given an input or set of inputs. They control the flow of information through the network. Okay, they decide whether it'll be activated, whether its output should be passed forward to the next layer. Biases and activation functions work together. Okay, so they transform input signals. So what do I have? I've got every neuron receives input data, a weighted sum of the inputs in the previous layer plus a bias. Okay. The activation function processes this sum. I've added up the weighted sum and the bias. Then the activation function picks that number up and it produces an output signal or not. Okay. There are a whole lot of activation functions. I don't want you to worry about this. This just happens to be one of them called swish. There are a lot of them. By the way, your GPT or Claude will suggest an activation function to you. Use that throughout your neural network. Don't start switching activation functions in nodes. In layers. All right, so here's how it works. Inputs coming in, they have weights connected to them. You perform the weighted sum of all the input connections. You add the bias to the sum. Now, biases can be negative. Okay, then your activation function picks up this sum, and you have an output. Okay, as soon as you get the output in the output node, it does an error calculation. The amount and direction of the error starts the back propagation process. Okay. Now, we'll work out an example here in a minute. So feed forward back prop, it's a type of neural network. It learns complex relationships, obviously, between inputs and outputs. Really good for recognizing patterns and making predictions. Okay, this is good. Every time it cycles through, it refines its initial parameters, bias and activation functions, and weights coming through the system. All right, feed forward, it goes left to right, input to output. Okay, back propagation, that's where you learn, and I'm getting the amount of difference between what I'd expect to see and what the network says, and that generates back propagation. All right, now, input layer doesn't do a thing. Developers feed the training data to the input layer. Now, they don't have weights or biases. Their only function is to pass that data. Okay. Input layer, the first hidden layer, they've got a weight. We showed you that. The weights can be positive or negative. Biases determine the difficulty of the neuron sending a signal. Notice, if a bias is largely and negative, it subtracts from the sum of the inputs, and that makes it harder for the neuron to reach its activation function threshold. Okay, so in other words, I've got every connection that comes into the neuron has a weight associated with it, and you're gonna have the sum of those weighted inputs. Then the bias is added or subtracted depending on the size of it. So if it's large and negative, that lowers the value, which means it'll be harder for the activation function to fire. In other words, send the results to the next neuron. Notice, if you've got a large negative bias, by the way, these biases are determined by the neural network. So if I've got a large negative bias, it can help the network focus on specific patterns, but this means that it might only fire when it finds something very important. Well, that's good, depending on what you want to do. You may not want to do that. You may want to be more inclusive. Okay, if it's a large positive, that adds to the sum of the weighted inputs, and that makes it easier for the neuron to reach its activation function and fire. So what do you get? It'll respond to a wider range of signals, and you'll get less obvious patterns. You can pick up patterns that are not immediately obvious. So you get to decide, do you want to go deep with a specific pattern, or do you want to get broadly inclusive? Okay, now, how do developers start this? They initialize their neural networks. These are data scientists, folks, and they randomly set weights between the layers and assign biases. Okay, they use small random values. Once the inputs reach the first hidden layer, every input is multiplied by its corresponding weight, summed up, add the bias, and that goes through the activation function. Now, after it makes a prediction, when you got all the way through and you're out the output layer nodes, you say you're going to make a prediction. It calculates the error, difference between predicted and active values. Outstanding. That's your loss function. That function starts a process of back propagation, which means go all the way back, pull in the next data. The back propagation function has changed all the weights and biases already. Now I just run it again. So what do I have? The back propagation process. Notice the weights of each pathway and the bias values in each node are changed by the network in anticipation that the next iteration will reduce the error. Okay, I'm looking for smaller error or loss upon the output. Okay. Now, you have this magnificent data set here. GPAs, starting salary, 3.42, 78,250, etc. And you say, okay, let's run this into a neural network. Now, what do you get? We're going to train the neural network with the first three instances here, GPA and starting salary. Then we're going to test it with the 3.70, okay, the last row of data. Now, here you go. 3.42, that's your first GPA, comes in, input node. All it does is transfer this 3.42 up this path and this path, because I've only got two neurons in my hidden feature, hidden layer. What do I get? 3.43 times 3.42, and then add the bias. So 3.42, 3.42, say 11 minus 1.27 gives me a 10. Here, I multiply 3.42 by 0.875, add the bias. I'm going to use the activation function as swish. Whatever that sum is, notice, I need the sum of 3.42 times 3.43 minus 1.27, whatever that number is, then it goes this way and you multiply it by 4.09, add the bias. Okay, this is great. This one comes this way, does the same thing, whatever that number totaled out to be, multiply by 5.37, subtract this bias. Now, if you do these numbers, you get 62.012. What did I expect to get? 78.250, because that's what the starting salary of this person, what they noted. So I'm off by minus 16.238. Okay, that is your loss value. This is your loss function. And it dictates, as I come right back around, go all the way over here, I'm off by quite a large number there, probably looks like 20%. So I come over here, and all the next data that comes in will be 2.63, but these weights and biases have now been changed by the neural network. So this is your feed forward part. The back propagation, I'm pretty far off. So they're going to make some pretty interesting changes in these weights, all four weights, and these three biases. For our purposes, we're just going to leave the activation function as swish. Okay. By the way, the large language model that you use will suggest activation functions. All right. Now look, that's the first iteration. There's the second one. I mean, this is the first one. If you go through what we just did, this is the description. Okay. So what did I look at here? 3.42 times that weight of the weight of 3.43 multiplied by the person's GPA, 11.371, adjusted with a bias. I subtract 1.27 and get 10.461. Okay, so it just goes right on through. Second iteration, that's the first one. First iteration. I don't know why I did that twice. Second one, 2.63, the GPA comes in, get all the way over here. The result's 37.168, doing the arithmetic. I'm off by minus 12. Comes back over. See that written down. There's a third iteration. The 4.0 comes in, goes through. Loss function is still 11. Okay, minus 11. Go to fourth iteration. And I'm down to 8.309. All right, now, this is the fourth iteration. That's your test. Okay, because remember, we're going to use the first three for training, and then the test was a 3.70. So I've got, not too disastrous. So I'm checking to see if it's accurate. So I do all this, And I say, okay, great. Lower pathway does this, just 6.14, transferred values continue to the output layer. And I have minus 8.309. So I say the prediction is about 89.6% accurate, 71.49 divided by the 79.8. And so if fixed, the neural network might lead a little bit more training data. That's exactly how one of these things works. Now, that's exactly how a neural network works. In your case, the large language models will walk you through this. The reason I want you to do this is you'll see some interesting results in what you get in your output layers, which is kind of useful after you've run your data set through all the other algorithms. So you get to do that comparison. That's a nice, simple look at one type of neural network. Okay, there are a lot other more complicated ones, if you will. All right, same data set, drop churn, and use all the other features. All right, here we go. Make sure that you have scaled your values, okay? It's always better to standardize everything in your data set. It'll really help the neural network converge. You're going to split, again, 80%, 20%. Now, building the neural network. This particular neural network that was set up with me consulting with GPT, the structure goes from 32 neurons in the input layer to 16 neurons in the hidden layer to 1 neuron in the output layer. Okay, why is there only one neuron in the output layer? Because you're only going to get a probability of churn or no churn, so it's going to be a value between 0 and 1. Okay. So this line of code creates that neural network. By the way, I gave it DF head, the data set we've been using, and I just asked it, I want to build a neural network. What's your recommendation? It gave me sequential because I want to work left to right. Here's the input layer. I want to add the first layer. All right, we're going to use dense. Then we're going to use 32 neurons in the input layer. And dense just simply means that every neuron connects to every neuron in the next layer. Okay? Much easier to just use dense instead of getting too complex. This particular line of code sets a number of input features, which is fine. Input there is your X value, your X features, your independent variables. Activation function, it suggested ReLU, and guys, I don't care what activation function you use, it's better to go ahead and use what your model suggests. Then your hidden layer, it'll add the hidden layer for you. You're going to use dense, fully interconnected, only 16 nodes, same activation function. Then you're going to get an output layer. Again, what have I done? Output layer, I only want to have, it's going to be dense, fully interconnected. I'm only going to have one neuron activation sigmoid. It suggested sigmoid because it's much better to use this to squeeze the output between 0 and 1. That was its suggestion. Next, you're going to compile the model, okay, with this one line of code. Okay, what have I got? I'm going to minimize prediction errors and loss. Okay, you're using feed-forward backpropagation. Now, binary is a loss function that measures how wrong our predictions are here. The optimizer, this particular one, is ideal for binary classification. Optimizer atom adjusts the network's weights. There are other optimizers you can use. Use the one that's suggested. I used accuracy for a metric, obviously. All right, what have I just done? I've compiled the model. Now I'm going to train it. There it is. Model fit, training data. Okay, what you have to decide here are the number of epochs and the batch size. Okay, epochs, the number of cycles it's going to take through all your data. Okay, an epoch means if you guys have 300,000 instances and 30 or 40 features, then you might want to go with epochs 20 or 30 or 40 and just see if it converges. Okay, batch size 32 instances at once. Then it's going to give validation data as your test data. You're going to need validation data. Okay, 2 hyperparameters, epochs and batch size. We went through that. Then what you'll see is this is what you'll get. Run through all the epochs. Then you'll see model fit, epoch size, and you get the, there's a whole lot more of these, of course. You can see all the way back up and down. Okay, because I specified 100 epochs. I don't know why I did that. But it did converge. So when I look, I want to check between epoch 1 and epoch 100. This is the progress of the training batches. So what do I have here? The very first epoch, which goes through all the data, accuracy of 0.66, the training loss is whatever they're talking about there. Lower values indicate better model fit. Naturally, you get 0.763 is pretty high for a first epoch. That's perfectly normal. The validation accuracy, it's okay. 81% accuracy on data is not seen, predicting churn or not churn. And then you get validation loss, which is, it's a little bit, it's getting validation metrics better than your training metrics might indicate an unusual pattern. Don't worry about that. I just put it in there just in case you run into it. All right, I'm in the last batch now, the last epoch. Okay, where am I? Accuracy's gone to 0.81. Not great, but much better than the first one. Your loss has gone down, improving a better fit naturally. Validation accuracy is about the same. Okay, validation loss. And so then I come down and I said, okay, I want to look at the evaluation. So I want to check accuracy, 0.81, which you would expect. And then you, of course, can, if you decide to do this, it's fine. I just put this in there for discussion as far as if you want to see how this is the training accuracy and this is your validation accuracy and this is epochs and then training loss and then validation loss. And that's optional. Okay, if you guys don't want to play with that, don't worry about it. All right, so we'll talk about that on Monday briefly, and then that's all the algorithmic literacy I want you guys to have. If I had to pick something that you guys should stick with, cleaning. Okay, your conversations will be, as business professionals, you'll be talking mostly to the analysts, but I will guarantee you will have conversation with the data scientists, okay, especially on strange things that happen. And Lord knows we have examples of that, okay? All right, see you guys on Monday.